All right. So now the question is, I haven't told you which node of the nodes that are found and not handled, what order do we do them in, right? So what are the obvious orders? You got a stack, you got a queue, you got a priority queue, right? What's a stack? Is you do the one that you saw most recently. A queue, you do the one who's been around the longest. A priority queue, you do the one that seems the most important to you. All right? So queue, yeah, let's just handle the one that's been around the longest. And why, if it's been around the longest, then you probably found, you found it the earliest. It's probably the closest to S. So let's go there, and that's going to be breadth first search, right? And right, you in your test 2, test 3, one of your programming tests, you were supposed to do a breadth first search, which to me is kind of weird because we hadn't covered it. But now we're covering it. Not that it's going to do you any good. And he also said, don't use a queue, which is kind of funny because for me, breadth first search is queues. But it was also easier because it was on a tree, not on a general graph, right? So there you have it, right? So we're gonna talk about these depth first searches. Breadth first searches is you handle them one layer at a time, right? You handle them in the order of their distance from S, right? All the ones that have 1 edge, 2 edge, 3 edges from S, right? Priority queue is we're going to have an estimate of how close so now when we're here, we're going to add weights to the edges, right? If you were doing Google's, how do you get from here to my house? You're going to have lengths of edges, and we want the path that's, in fact, Google will give you the path that's shortest time, right? And so the priority queue will be based on how close you think it is to S. And then that's Dijkstra's algorithm, which gives you shortest path. And then a stack is you're handling the one that you've seen the most recently. And that means you just keep going. The one that looks furthest, and you're going to follow these paths. You're going to go until you bottom out. And that first search is also really useful. And I would almost say depth first search is used more often than breadth first search. But all right, so what we're going to do now, and it's not going to take very long, is we're going to cover queues, and then we're going to skip over this and cover stacks, and you guys can decide whether you want to learn Dijkstra's algorithm or not, because it's harder. Just to let you know, the other sections aren't doing graphs. So we can collectively decide whether I'm going to put an extra question on graphs for you or not. Let's just say right now there won't be a Dijkstra algorithm question because it's harder, right? And these others are pretty easy. All right, so what we're going to, again, what we want to prove is that we find them in the length, in the order in which their distance is from S in terms of number of edges. And since the loop invariant says, what have we done so far? We're going to just say, so far we've done them in this order, right? And I'm going to give you the algorithm by doing an example. And you'll all say, yeah, that's obvious, right? So we start off with S has been found. And, we also label every node with how far it is from S, right? D, distance, right? So S is distance 0 from S. And then I put a green line here. Why? Because those are all the guys that are distance 0 from S, right? And then we're going to handle the guys distance 0 from S. And So we found all its neighbors, and we put them in the queue in some order, right? And then we're going to say, oh, those guys are all the ones that are distance 1 from S, right? And then we're going to keep going. We're going to handle these nodes one at a time. And remember when you were doing test 2, you were supposed to go one direction and then back, and right? So these ones, you might go forward, and then the next ones will go back, right? So let's go forward. We handle A. When we handle A, right? Oh, because here A comes off the queue, and A's neighbors go on the queue, right? And now we're going to handle D. So D is going to come off the queue, and D's neighbors go on. But you'll notice F is the neighbor, but F is already on there, so let's not put them on there twice, right? And then we handle G. What's G going to give us? I guess G is going to give us J, right? And then we're going to handle B, and we've already had G, but we're going to get E, right? Everybody see that? Oh, we had E already, right? And now we've handled everybody at distance 1. And so what do we know? We got everybody at distance 2, right? And so then we say, that was great. Those are the distance 2 guys. And now we keep going. We handle C, we handle F, we have M, right? We handle each of them. And as we handle them, we find their neighbors, right? And so now we've handled all the guys at distance 2. Well, what do we get then? It gives us all the guys that are distance 3. And I might say, how do I know there's a path length 3 to these guys? Well, because we kind of traced it, right? We went from 0 to 1, then we went from 1 to 2, right? So we know there's a path of length 3 here. How do we know that there's not a shorter path? Well, kind of from our loop invariant, if there's a shorter path, you would have found it earlier, right? So and then we handle these, right? We handle H and L and K, right? Then we just got K, and then you handle K. When you handle K, there's nobody, so there's nobody distance 5, right? Everybody kind of, and then this is sort of so this is just the nodes, the edges that are in the tree, right? There may be lots of other edges that we don't know about, but you can kind of see that when we're doing it, we're doing one layer at a time, right? So these guys have already come off the queue, and what's on the queue are these nodes of distance k and these nodes of distance k plus 1. And when we handle node U is the front of the queue, and when we handle it, it leaves the queue, and all of these guys go on the queue, right? Does that make sense? And it's pretty straightforward, right? Everybody kind of buy that? And so our post condition is that we handle them in their distance. And why? Because how do you know there isn't a shorter path? Because we would have found it earlier, right? Everybody buy that? All right, so now what we want to store is we want to store that tree. What we want to store is for every node, the shortest path from S to that node, right? And you can think, well, we have n nodes, and each node we have to store a path. How big is that path? That path might have length n, so that's n times n, so that's n squared data structure, right? And we don't want to do that because we're lazy. We want to store for every node just a constant number of things. In fact, what we're going to store is the parent in the tree, all right? So people often use pi, maybe pi for p for parent, right? So in this tree, if you go over to you find V, and then you say, well, who's V's parent? Well, at V, we store pi of V, which gives me the parent. And then at this node, we store its pi, which gives me the parent. And so you just keep following the pi's, which leads you in a path back until you get to S. Right? Does that make sense? And so how do we do it is, suppose we've already found U and use distance D, and then we handle U, U's at the top of the queue, so we handle it, and we follow this edge to V, and now what's D's, if V's never been found before, there's no shorter path to it, then we say, hey, I found a path of length D plus 1. So you give it, it's the value D plus 1, right? And what's the pi? And then we assign a pi value. What pi value do we assign? P of, so it's going to be, it's the parent. So the pi of U, well, it's back here somewhere. We've done that already, right? So pi of V is going to be U, right? Does that make sense? Right? As we find V from U, we can say, who's V's parent? V's parent is U, right? So here we're just, what have we changed in the code? We've changed that, somewhere it says Q. Anyway, these things are a Q. Oh, here, there's the word Q. And we take U from the front of the queue. And if V hasn't been found before, then as before, it's now found and not handled, but we give it a D value. When we find it, we give it a D value and we give it a pi value.